Hello students, welcome to Scholars and Curious, and we will study or discuss today about periodic potential and Bloch theorem, and the whole basic starts with the band structure. So we'll start with isolated atoms. The electrons of a single isolated atom occupy atomic orbitals, which form a discrete set of energy levels. You can see in this diagram. These are the discrete set of energy levels, different energy levels. Thus, in solids, the levels from continuous bands of energy rather than the discrete energy levels of the atoms in isolation. So, this type of structure is found in isolated atoms. When we talk about the diatomic molecules, this is a bound state. So in a bound molecular state, the energy varies from the sum of energies of two atoms separately for large. These are the two atoms separated at a small distance, and when the energies increase, they are like the continuous band. Okay, so this is the structure for the diatomic molecule N. So the same structure is for four closely spaced atoms. We can see this is one isolated atom, then two, then three, and then four. Here are four closely spaced atoms. Let's see here. This is your valence band, okay, and there is some energy gap. We can see here there is some energy gap. Yeah, and then this is your conduction band. So between conduction band and valence band there is some energy gap, and the same type of arrangement is found in crystals having n atoms. So we can here understand the band spacings in insulators and conductors. Now the first figure is for insulator. In this, conduction band and valence band have a large energy gap, which forms the insulator. The second figure is for semiconductor. Semiconductors have the energy gap in the order of 1 electron volt, approximately equal to 1 electron volt between conduction and valence band. And in the third figure, this is for conductor. The conduction and valence band are overlapped, no energy gap between them. So how to choose EF, that is called Fermi energy, and behavior of the Fermi function at band gaps. So this is your Fermi function. We can say Ne equals to 1 over exponential E minus EF of kT plus 1. E is the average energy and EF is the Fermi energy. This is your Fermi energy, EF. And this graph is the Fermi distribution for a selected Fermi energy. We can understand it by this. We have to choose or know about the Fermi level or the energy of the Fermi level in insulators, conductors, and semiconductors. So there are three different figures. A is for metals. This A is for metals. We can see and we know the energy gap between valence band and conduction band is 0. They are overlapping each other. So where does the Fermi energy should lie? The Fermi energy will lie between these two bands here. Here it is, EF. So we can see here that this is the fully filled band. Valence band is fully filled. Conduction band is also filled with the conduction electrons. So for the fully filled band, the Fermi energy is the highest energy. You can see at this level Fermi energy will lie. So it is the highest energy for this fully filled valence band. Now let's come to the insulator. B is for insulator. There is a large energy band gap between conduction and valence band. Large energy band gap. Now, again it is not. Now we can see that the EF should lie here in between this, and we can see that it is not fully filled because there is a gap. So for unfilled band at t equals to 0, the Fermi energy will lie in between the conduction and valence band. Now the same is here for intrinsic semiconductor. The Fermi energy will lie in between the conduction band and valence band, because now here again both are not fully filled. Okay, so we can say if in unfilled band EF is energy of highest energy electrons at t equals to 0, if in filled band with gap to next band, EF is the middle of gap. Moving ahead, let's see about fermions in Fermi level at t equals to 0. Here is a conduction band and here is a valence band. At absolute 0 Kelvin, for a Fermi level, for a semiconductor, the Fermi level will lie in between the conduction band and valence band. So if we say this whole gap is E gap, then the energy from here to here will be E gap divided by 2, because this Fermi level is dividing this total E gap into two parts. E gap by 2 for here, E gap by 2 for here. Now, if we are increasing the temperature, so what will happen? So, fermions at T greater than 0. So, in the first diagram, we can see no electrons can be above the valence band. Fermi level is here. At T greater than 0, we see in the case of semiconductor, some electrons get free and get out from the valence band, which wanted to go to the conduction band for the conduction of electricity. But we can see the Fermi level is here for the semiconductors. So, fermions at temperature greater than 0, when we are increasing, the valence band will increase its height. Now, in the second diagram, the Fermi function will mold itself like this. Some electrons can have energy above the Fermi levels. Some of the electrons can cross this level. This was your Fermi level, and some electrons can cross this barrier. In the third step, we can see when we are increasing temperature again, then electrons can penetrate into conduction level. So at high temperatures, some electron can reach to the conduction band and contribute to electric current. So here the slope is more in the third case of the Fermi function. So this is how the Fermi level and Fermi energy can work in the semiconductors. Now, in intrinsic semiconductor, either it is silicon or germanium. As I told you earlier, the Fermi level will lie in between the conduction band and valence band. Whatever the concentration of electrons or holes, whatever the range of band gap between the bands, the Fermi level in intrinsic semiconductor will lie always just between the conduction band and valence band. So for silicon and germanium, we can see the same. Now we'll talk about energy bands and energy gaps in a periodic potential. So this diagram is denoting the periodic potential. The atoms are here, here and here, and they are in periodic potential. This is your periodic potential. What I mean to say when I am saying periodic potential? Periodic potential means the same condition again and again repeating itself for any potential, for any system. And in crystalline solid, when we talk about the solids, then the atoms arrange themselves in a periodic manner. The atoms arrange themselves in a periodic manner in a crystal. That is why the potential they follow is assumed as periodic potential. And to solve the periodic potential, there are some theories. One of them we'll study today. So along a line parallel to this and running between the atoms, the divergence of periodic potential energy are softened. We can see this is the diagram between the distance and the potential energy. So the periodic potential looks like this one. This is a periodic potential. This is a simple 1D mathematical model. For this model, the function for the potential energy is this: Ux equals to U0 plus U1 cos 2 pi x by A, where U0 and U1 are less than 0. Let's specify this periodic function. So, electron wave functions in a periodic potential have some cases. If U1 equals to 0, so wave functions are plane waves and energy bands are parabolic. And the wave function has the form psi equals to A exponential eta kx minus omega t, and energy E equals to h cut square k square by 2m. Now, if U1 is not equals to 0 and k is less than pi by A, then electrons' wavelengths much larger than A, so wave functions and energy bands are nearly the same as above. If U1 is not equals to 0 and k is less than equal to A, not much smaller, k is less than equals to pi by A. So electrons' wavelengths approach A, so waves begin to be strongly backscattered. And the wave function will have the form psi plus minus equals to A exponential eta kx minus omega t plus minus B exponential minus eta kx minus omega t, where B is less than A. If U1 is not equals to 0 and k equals to pi by A, electrons' waves are strongly backscattered. That means Bragg scattering. So standing waves are formed, and the wave function will have the form psi plus minus equals to C exponential eta kx minus omega t plus minus exponential minus eta kx minus omega t equal to 1 by under root 2 a exponential eta kx plus minus exponential minus eta kx exponential minus eta omega t. Let's introduce the origin of bands. Electron in vacuum we can see in the diagram left, and the Schrödinger wave equation is on your screen. Let's select some pointer. This is the Schrödinger equation in which we can write hk phi equals to ek phi, where k is the momentum vector, E is the kinetic energy, and m is the effective mass. Now, this hk will have the form of energy in the form h cut k square over 2m, which is free electron kinetic energy Hamiltonian. Now, the solution of this Schrödinger equation will take the form in the graph Ek, which is called Ek dispersion relation. This graph is continuous and for continuous energy band, where k is the momentum vector and A is the kinetic energy. This Ek will have the form E equals to bk square, where b is any constant and this is Ek relationship. Ek relationship has the definition of eigenenergy. This ket of phi is eigenvector. Eigenvector for plane wave have the form phi k equals to a exponential minus eta k r. Now, when electron is in a crystal, the Schrodinger equation H ket of phi equals to Ek ket of phi will transform, and this H will be now H cut k square over 2m plus Vppr. Vppr is periodic potential, and the same graph we have seen earlier. The electrons in a crystal are arranged in a periodic manner, and that is why the potential they have is periodic potential. We are denoting it here by Vpp. And the electron in crystal and the Ek diagram, having the Ek diagram, they have this continuous energy bands. You can see in this graph that there is discontinuity, and after a certain range there is a gap. Eigenvectors here are no longer simple plane waves as we have seen earlier. Energy bands now have become discontinuous, and they are producing band gaps. So how to solve for electron in a crystal or in 1D crystal? This is our periodic potential. Now we know that how this types of graph is coming, because the electron in the crystal is moving in a periodic manner, and the crystal potential is periodic potential. Now the solution can be obtained as a periodic potential problem. There are two ways. The first one is the chronic-Penny model. And for the same, to solve the single electron periodic potential Schrodinger equation, we'll follow the Bloch theorem, in which the periodic potential can be written as Vx plus A equals to Vx. And the wave function psi k can be written as psi k x plus A equals to exponential eta ka Vkx. This is the electron eigenvector, and the electron eigenvector follows this relation due to periodic potential. This is known as the Bloch theorem. So what is the Bloch theorem? A theorem that specifies the form of the wave functions that characterize electron energy levels in a periodic crystal. Bloch theorem states that solutions to the Schrodinger equation in a periodic potential take the form of the plane wave modulated by a periodic potential. This is our Bloch function psi r equals to exponential eta k r ur. And this is the schematic of real part of typical Bloch state in one dimension. Let's move ahead. How the Bloch theorem looks like. In the presence of a periodic potential Vr plus r equals to Vr, the wave function takes the form psi r plus r equals to exponential eta k r psi r, where r in 3D is n1 a1 cap plus n2 a2 cap plus n3 a3 vector, where r vector in 3D form is n1 a1 vector plus n2 a2 vector plus n3 a3 vector. Let's have some proof. This is the proof of Bloch theorem in 1D. In one-dimensional, we will consider R equals to Na. This is the periodic array of the atoms in one-dimensional crystal, and the atoms are feeling the periodic potential. So in 1D, we can write periodic potential as Vx plus R equals to Vx. Then, according to our Bloch theorem, psi x plus r will be equal to exponential eta k r psi x. Let's define translational operation TR. we are applying it to the Schrödinger equation dr hx psi x. We can write hx as hx plus r and psi x as psi x plus r. Our hx plus r will be hx because no periodicity will be in Hamiltonian only. Psi x plus r is psi x plus r again. By translating this, we are getting hx dr psi x. That means dr and h are commuting each other. dr and h equals to 0. And that is why we can write as dr psi x equals to psi x plus r. Let's introduce some constant Cr and then psi x. If we are doing mod of square of psi x plus r, then we are getting mod of Cr square psi x mod of square dx. Let's have this quantity Cr mod of square as 1 and let's consider this Cr is equal to exponential iota theta r. Then this mod of psi x plus r square dx will be equal to mod of psi x square. And likewise, we can do for psi x plus 2a, psi x plus 3a and so on. And in that manner, we can have psi x plus r equals to exponential iota kr psi x with any constant Cr. Another form of the Bloch function is this. Psi kr equals to exponential iota kr ur, where ur plus r equals to ur. This is your periodic potential. ur plus r equals to ur. And this is a two-liner proof. Psi k r plus r, you can write it as you are putting just r plus r instead of r vector. So just put on the both place of r plus r. Then separate out both exponential iota k small r and exponential iota k capital R. And ur plus r is ur, you know from this relation. Now this exponential iota kr ur will be equal to psi r. So this will remain and this will again follow the Bloch theorem. So this proof is important. If you want to solve the Bloch theorem, then what is the Bloch theorem and what is its proof? You should know all these things. Now let's have any system with spherical symmetry. Let's consider it for hydrogen atom. In hydrogen atom, Vr is used to be equal to Vr, spherical potential, and we know that for the system with spherical symmetry, HL square commutator is 0 and HLZ commutator is also 0, and H psi ln is equal to E nlm psi nlm. And again, for L square, the value we get is LL plus 1. For LZ, we get MH cut. For LZ, we get MH cut, where our psi is used to be psi nlm r theta phi equals to r nlr y lm theta phi. What is the meaning of lm is y lm theta phi. If we are using y00, then y00 is 1 over under root 4 pi. y11 is minus under root 3 by 8 pi exponential iota phi sin theta, and so on. Let's introduce a periodic potential in the system. That means the same system with translational symmetry. So with translational symmetry, the potential will convert into periodic potential. Vr plus r will now be equal to Vr. Now H and T will commute. H and T will be equal to 0. And H psi k will equal to be E n k psi n k. T r psi nk equal to be exponential iota kr psi nk, where psi nk will be according to our Bloch theorem, psi nk equal to exponential iota kr unk r. In a normal spherical symmetry, for example hydrogen atom, the wave is like this, but with the periodic potential, the wave will follow this diagram. You can see here. So this is one of the example. Now let's solve some questions. These questions here are from previous year CSIR-NET JRF and GATE papers. Question 1 is, consider an electron in a BCC lattice with lattice constant A. A single particle wave function that satisfies the Bloch theorem will have the form Fr exponential iota kr with Fr being. He is saying that there is an electron in BCC lattice. So to solve these types of questions, two things we should know. The first one, what is Bloch theorem, and the second one, what are the primitive wave vectors for BCC lattice. Let's solve this question. So for BCC lattice, the primitive vertices are, you should remember these three primitive vertices for BCC lattice. A1 equals to A by 2 minus I cap plus J cap plus K cap. A2 equals to A by 2 I cap minus J cap plus K cap. A3 equals to A by 2 I cap plus J cap minus K cap. And the second thing you should know about the Bloch theorem. So for Fr equals to Fr plus A, and A is a lattice vector, that means Fr is periodic with respect to the translational vector. So one by one, we'll choose an option and we'll apply our Bloch theorem. So here we have chosen option number B. You can do the same for option A, C and D. So this is our option number B, that means our function. Just what we have to do, we will replace Fr by Fr plus A1. What we have A1? A1 is A by 2 minus I cap plus J cap plus K cap. So for x plus y, we will write it here, the coefficients of I cap and J cap, that is minus A by 2 and plus A by 2. For y plus z, we will keep here the coefficients of J cap and K cap, that is plus A by 2 and plus A by 2. And for x and z, we are keeping here the coefficients of I cap and K cap, so minus A by 2 and plus A by 2. And then we will solve this. While we will do mathematical, we will find Fr plus A1 will be equal to F or Fr, means the same from where we have started. We will do it for the lattice primitive vector A2. The same process will be for A2. We will get again Fr plus A2 equals to Fr. The same process we will do for A3, and we will again get that Fr plus A3 equals to Fr. And combining three of them, we will get Fr plus A, where A is A1, A2 and A3. So Fr plus A will be equal to Fr. That means this will be periodic, and the other three functions will not be periodic, and that is why the correct answer will be option number B. These types of questions mostly come into the exams related to the physics. My next question is from GATE 2010. The Bloch theorem states that within a crystal, the wave function psi r of an electron has the form. They are asking just the statement of Bloch theorem, which is option number D. We know that this is one of the form of the Bloch theorem, which states that psi r equals to ur exponential eta kr, where ur equals to ur plus a. A is a lattice vector and k is an arbitrary vector. Question number 3. Consider a one-dimensional lattice with a weak periodic potential ux equals to u0 cos 2 pi x by a. The gap at the edge of the Brillouin zone k equals to pi by a is. We have to calculate the gap. So how to solve these types of questions? We have given the function, the periodic function, the periodic potential u equals to u0 cos 2 pi x by a. What we'll do? We'll just put first x equals to pi by a. We'll just put first this x equals to a by pi and again x equals to 0. And then we'll get the result. So energy at the edge of Brillouin zone is ut equals to u0 cos 2 pi by a, and we are putting x equals to a by pi. Some conditions or cases we have studied about the periodic potential, in which one of the case was that if u1 equals to 0 and k is equals to pi by a, then we'll put this type of periodic potential. So this a and pi will cancel out each other and we'll get the simple value. And energy at k equals to 0 ub is u0 simply because cos 0 is 1. So band gap is the difference between these two energies. So delta U will be ut minus ub, which will equal to minus 2u naught. And thus the video completes here. Thank you for watching. Please like, subscribe and share my channel. Keep supporting, keep studying.